Hi everyone. This video is going to provide an overview of symmetry in geometry. There are several types of symmetry, but we're going to talk about two of them. And the first one is called reflectional or line symmetry. A figure has reflectional symmetry or line symmetry if it can be reflected across the line of reflection and look exactly as it did before the reflection. In other words, if you take the line of reflection and you fold the figure over the line of reflection, it would fold on top of itself. So here are some examples with some common figures. The block letter T has a line of reflection right here. I'll call that L for the line of reflection. If you fold that letter or flip it over the line of reflection, it would fold on top of itself. The line of reflection for this, I don't know what you would even call this. It's a figure, right? So a geometric figure. There's my line of reflection. Again, if you fold it over top of that line, it would fold on top of itself. Here's the line for L, for M, the block letter M, and for the arrow. They each have one line of reflection. This figure down here has several lines of reflection. I'm just going to sketch them in for you. So first of all, if I reflect this figure over this line right down the middle, right, there's line 1. If I reflect it over that line, it would reflect on top of itself. But there are other lines of reflection in this one. If you fold it over basically this vertical line, and fold it over that line, we'll call this L1, this would be L2. There's one. You could also have lines of reflection that are diagonal. So if you fold it over that diagonal, L3, or this diagonal, the diagonal going in the opposite direction, L4, if you folded that figure over any of those lines, it would fold on top of itself. So it has 4 lines of reflection. You've got to be a little careful about lines of reflection. Things that you think would have essentially reflectional or line symmetry, they have it some, but not a lot, not sort of a ton, if you will. So for example, this rectangle does have a couple lines of symmetry. If I draw a line of symmetry here and reflect it over the top of itself, if I draw a line of symmetry here and reflect it over the top of itself. So those 2 lines of symmetry. But how about the diagonal? I'm going to eliminate what I just did there, erase that, and I'm going to draw the diagonal in on this. So the diagonal would look like this. And is that diagonal a line of symmetry? Turns out it's not. Because if you fold this figure over the line, this point down here, anything that's on the line, by the way, it's called a stationary point. It's not going to go anywhere. Okay, when you fold it, it's going to stay right there. But this line right here, when you fold it over, it's going to come down. It goes over there. It folds down this way. It would look like that. Okay, this line would go like that, and then this corner, again, if you fold it over that line of reflection, it would fold up to here. So it would look something like that. So if I folded that line over that line of reflection, I'd get this rectangle here. In other words, it doesn't reflect on top of itself. So the diagonal would not be a line of reflection. You might want to check as well for this parallelogram. And you can just basically cut out a parallelogram if you like. Try to fold it over this line of reflection. Again, it's not going to fold on top of itself. This top point is going to come down to about there. So it's not going to fold on top of the figure. A nice investigation when you have regular polygons is how many lines of reflection do they have. If you have an equilateral triangle, it has 3 sides, then it actually has 3 lines of reflection. Line 1, 2, and 3. So 3 sides, 3 lines of reflection. A square has 4 sides. It's a regular polygon, a regular quadrilateral, and it has 1, 2, 3, 4. So 4 lines of reflection. A regular pentagon. Now again, the lines go all the way through. It has 1 line, 2 lines of reflection, 3 lines of reflection, 4 lines of reflection, 5 lines of reflection, and that's it. Because this would be number 1, that would be number 2, and so forth. So it turns out for a regular polygon, the number of lines of reflection equals the number of sides for a regular polygon. The second type of symmetry we're going to talk about, at least in this intro, and there are others, by the way, there are other types of symmetry, is rotational symmetry. And rotational symmetry means that if you rotate a figure about a center of rotation, so it has to have a center of rotation, and some number of degrees, the degrees of rotation, again, it will rotate exactly on top of itself. So for this square, I've got a center of rotation here. I'll call that C. If I think of kind of putting a pen or a pin down on that and spinning the figure around, if I spin the original figure 90 degrees, it would go back onto itself. So you notice S is like where it starts. If you spin it 90 degrees, it would go back onto itself. If you spin it another 90 degrees, now keep in mind that's going to be the first 90 and the second 90. So this would be 90-degree rotational symmetry about the point of the center. The second one would be 180-degree rotational symmetry. That also rotates on top of itself. If you rotate it 1, 2, 3 times, it also rotates on top of itself, 270-degree rotational symmetry. And then if you rotate it 1, 2, 3, 4, which would be 360-degree rotational symmetry, well, it turns out that everything has 360-degree rotational symmetry. So rotational symmetry, generally what you talk about are rotations between 0 and 360 degrees. A few more figures for rotational symmetry. How about this rectangle? Here's the original shape. I would rotate it about the center, and you can find the center of a rectangle by just drawing the diagonals. So this would be my center of rotation. That's important that you know what you're rotating it about. Think of it again, you sort of put your pen right there, or your finger, and then you spin the figure around. So if you rotate it 90 degrees, it's still a rectangle, but it doesn't rotate on top of itself. It has to be exactly on top of, basically look identical as it did in the original. So this rectangle does not have 90-degree rotational symmetry. But if you rotate it 180 degrees, right, so this would be 90, rotate it again another 90 degrees, it does have 180-degree rotational symmetry. You rotate it to another 90, so 270 degrees is not the same as the original. And again, everything has 360-degree rotational symmetry. So generally you talk about this rectangle having just one rotational symmetry, which is 180-degree rotational symmetry. And that's about the center P. All right. How about a few more? How about some letters? How about the letter M? Does it have rotational symmetry? And again, I would try to find the center. Let's call that center right there. If I'm rotating it, again, I kind of think of it, I'm putting a pin, right? So I put a pin down right there. There it is. There's our pin. And I put it down and stick it right in that center. And then I start spinning the figure around. So you spin it 90 degrees. Okay, it's still an M, but it doesn't look like it did originally. Another 90 degrees. So this would be 180-degree rotational symmetry. Doesn't have it, so it's no 90-degree rotational, no 180. Rotate another 90 degrees, so 270 degrees. Does not look like the original. So the only rotational symmetry I have is well, there is none. So this has no rotational symmetry. Other than 0 and 360, but we don't count those. A 0 means you don't do anything, right? So you don't move it at all. Everything looks the same as it does if you don't move it at all. So the M has no rotational symmetry. The last two, I've got two figures here. I've got a star, and notice the star, if I start here, I'm going to rotate it, and I'm going to rotate it basically that distance. It would rotate on back of itself. Rotate it again that same distance. It would rotate on back of itself. I just spin it around this center P right there. So what would be the degrees of rotation there? Well, there are 5 points to this star, assuming it's a perfectly symmetric star. There's 360 degrees in the circle, divided by 5, okay, and that's going to be 72 degrees. So the first rotation is a 72-degree rotation about the center P. I would rotate it another 72 degrees, so this would be in total 144 degrees rotational symmetry. So this star has 72-degree rotational symmetry, 144-degree rotational symmetry. Another 72 takes you to 216, would rotate essentially this point right here. Point A would be rotated down to this point. Another 72 degrees is, what is that going to be, 288 degrees rotational symmetry. And again, if you've got to have rotational symmetry between 0 and 360, everything has 360. So there would be 1, 2, 3, 4, and if you want to count the 360 degrees. Okay, but again, you generally don't count that. So there'd be 4 rotational symmetries, 72 degrees, 144, 216, and 288, all about the center P. The last one, this little recycling figure, looks like it should be symmetric, but if you look carefully, notice that this arrow has a little point to it. This arrow, the second arrow right here, so arrow number 1 has a point to it right on the end, right there. Arrow number 2 has a point to it, but arrow number 3 does not. So if you rotate, now if everything were identical, this would have, there are 3 rotations. That would be 360 over 3 is, there'd be 120-degree rotational symmetry and 240-degree rotational symmetry. And also, okay, but the figures are not the same. So if you rotate it once, say 120 degrees, this little arrow without, that arrow without the point is going to be up in this position right there. So it's not the same as the original. If you rotate it another 120 degrees, it would rotate the arrow without the tail, without the little points, would rotate to here. Still not the same as the original. So this figure, just because of the little details, has no rotational symmetry. All right. Thanks for watching. Bye-bye.